Assalamualaikum and hello everyone. We are from group 4 and today we are going to present chapter 3 sampling theorem. This is the list of our group members. My name is ADILAH and my fellow group mates no IZZATUL SYAZWANI, no Maisarah, no FATIN NAZIHAH, TERN CHIE, no SHAFFIQAH and ALIF HELMI. So for introduction, what is sampling? Sampling is the process of converting a continuous time signal to discrete time signal so that computer can process the data digitally. The discrete time signal Xn is obtained as a result of the products of the continuous time signal with a set of impulse x dt with period Ts. As you can see, this is the equation for the sampling.
Assalamualaikum and hi, my name is SYAZWANI BINTI RADZI. In this video, I will explain about the sampling process. As we know, the first is the sampling theorem state two important facts, which is the first is to represent an analog signal in the digital domain. The number of samples that we would need for each second of the signal should be more than the highest frequency represented by a signal. If a signal has a 10 kHz frequency component, then the sampling rates need to be more than 20 kHz. It is also stated that the analog signal need to be band limited to the highest frequency and cannot contain any frequencies above that. The sampling theorem states that to digitally represent this wave, we need at least more 2 sample points. So let's move to the sampling process by graphical representation in the frequency domain. First of all, we have to consider the continuous time signal xt. The spectrum of xt is a band limited to fm in hertz. For example, the spectrum of xt is 0 for magnitude omega greater than omega m. Sampling of input signal xt can be obtained by multiplying xt with an impulse train of period Ts. The output multiplier is a discrete signal that called a simple signal, which is represented with BINTI in the following diagrams. Sampling process also can be in mathematical terms when we derive the expression of Sn equals to xt that is equal to xt summation for negative infinity to infinity times t minus n ds. Then we convert it to Fourier transform. We got x omega equals to 1 over ts summation of negative infinity to infinity s dot omega minus n omega s.
My name is HELMI, and I will explain a little bit about the spectrum of sample signal. So the first one is called oversampling because the sampling frequency is greater than 2 times max frequency. And another one is perfect sampling, which is the sampling frequency is equal twice as max frequency. And last one is undersampling, where the sampling frequency is lower than 2 times max frequency. Increasing the sampling frequency will increase the storage space and processing time. The one we can conclude that when the sampling frequency increase, the storage space and processing time will also increase. This is about a frequency concept, which is the formula f is equal to 1 over t, which is inverse of time. It's called harmonic oscillation, which relate to the periodic motion. So for I don't have a calculator. Can I so this is simple. This where we get the frequency. If the t that we get from the graph is, we take it as 70. So 1 over 70. Then the frequency is 1 0.0142. So that's all.
Okay, next. There's two types of sinusoidal signal, which is continuous time and discrete time. So this is the continuous time sinusoidal signal. Okay, this sinusoidal signal which is defined for every instant of time. So this is the formula for the continuous time, which is A cos omega t plus phi. So A is stand for amplitude of the signal, which is the peak deviation of the signal from zero, and then omega, which is the angular frequency uh, in radians per second. So to find the omega, we can first you have to find the frequency. So next is time, and then plus phi. Phi is a phase in radian. So continuous time, we can say that all continuous time is a periodic signal. Okay, next, this is a discrete time sinusoidal signal. So this signal is defined only at discrete instant of time. So this is the formula for discrete time sinusoidal signal, which is A cos omega n plus phi. So A is still same, is the amplitude of the signal, and then omega is the angular frequency. Next, n is an integer counter plus phi. Phi is a phase in radian. So this discrete time sinusoidal signal may or may not be periodic because it depending values of angular frequency. So the difference between these two type of signal, we can say that continuous time signal has values for all point in time in some interval, but in discrete time, it has value for only discrete parts in next sampling of analog signal. So this is the example of uniform sampling, and this is the formula. So uniform sampling is a type of sampling that takes in or peak sample at regular interval of time from analog signal, that is at time instances that are equal to n times t, which n is an integer value, and this is period, which it is time interval between sample. The next formula to find the sampling rate, which is 1 over period, and the value must in hertz. So at here we can see the example of analog signal sampling. So at here we can see much clearer, which this is the sampling period, the red line, and this is the analog signal.
Sampling of analog signal. The relationship between Y and N is, for the formula, is T same as N per NT same as N per Fs. For the formula, the highest value formula is Fmax same as Fs per 2 or 1 per 2t. For the ohm max, the pi Fs or pi per t, while for the F or pi for the analog signal, while ohm for the discrete time signal. The next, for the sampling frequency. For the sampling frequency is Fs is same as 2F max. Nyquist sampling theorem. When the sampling frequency increases, the storage space and processing time will also increase. Aliasing will happen if the sampling frequency is reduced because of the overlapping between the reserved and replicated spectrum components. Fs are bigger than 2F max.
Good day, sir. My name is CHIE, and now I would like to present the Nyquist frequency. So what is Nyquist frequency? It is known as the Nyquist limit. So regarding to the Nyquist-Shannon sampling theorem, we know that the sampling rate, that is the Fs, must at least twice the highest waveform frequency, that is our Nyquist frequency. So from here we can see the equation Fs is equals to 2 times the Nyquist frequency. So from this equation, we can get the Nyquist frequency is actually half of the sampling frequency. Also, we know that the Nyquist frequency is equivalent to the maximum frequency of the audio waveform, and it is equivalent to the signal bandwidth that is shown on the diagram here also. So what happens if our sampling frequency is less than 2 times the Nyquist frequency? So this will lead to the aliasing effect. So what is aliasing? It is an effect that causes different signals to become indistinguishable when sampled. It means when our sampling frequency is less than 2 times the Nyquist frequency, so this sample frequency waveform will not be able to recover uniquely back to the original waveform. So here we can see, based on the diagram, the repeated spectra overlap, and in the overlapping region here will cause the permanent loss of the signal information here. So how do we avoid this aliasing effect? Firstly, we can ensure the Nyquist frequency is always in the range between 0 to half of the Nyquist frequency. So for example, we can run our audio waveform here through a low pass filter so that we can filter out the high frequency in the audio signal. And secondly, we can increase the sample rate, that is our sampling frequency Fs. And next, I will pass to the next presenter here.
Assalamualaikum warahmatullahi wabarakatuh. My name is Maisarah and I will present the example of the question for sampling theorem. So the question is, the signal x into t is equal to 1 over 800 pi x1t and x2t, where x1 into t is equal to sin 800 pi t over pi t and x2 into t is equal to sin 800 pi t over pi t. So the first question is, what is the equation of sampling for xt? So the answer of the equation of sampling for xt is 1 kilohertz. So the second question is, sketch the spectrum of the sample signal as s into t at the Nyquist rate of sampling. So if the s into t a sample at the rate of fs hertz, we need to use the radio frequency formula, which omega s equal to 2 pi fs radian set. Then we use this formula to get the formula of t, which t equal to 1 over fs second. So after we get the formula, we will find the xs omega at Nyquist rate, which omega s equal to 2 pi fs is equal to 2000 pi radian set. So this is a sketch graph that I have sketched. So we can see at the center of the graph is and at the negative side, the center is negative 2 and negative 2000 pi. So the last question is, sketch the spectrum of the sample signal as s into t at twice the Nyquist rate of sampling. As you can see, I mentioned the twice the Nyquist rate of the sampling. So we just need to multiply by 2. So we get the answer.
4000 pi radians Z.
So we need to sketch the graph. So the center of the graph is
Is 4000
same
pi
as the negative side, which is negative 1.
4000 pi.
So the gap between the graph, we call it as a gap length. So that's all for me. Thank you.
That's all for our group. Thank you so much.